Hello all, welcome back to another 65.0 tutor session. Today gets exciting because for the first time we are going to start actually putting code on this thing and executing code. So in the last episode we looked at how the CPU starts up. The long and short of it is there is a fixed location in memory that the CPU is hardwired to always load the starting address from. It's called the reset vector. It is at addresses FFFC and FFFD in memory, which is the fourth and third to last bytes, respectively. And we learned about storing numbers in big endian order, where the big part of the number comes first and then the small part. Do I have that right? Well, that would be big endian, but this would be little endian then. Sorry. So this is a little endian machine, meaning that if you wanted to store the number, let's say 1000 hex, you would store 00, and then at the next location you would store 0 or 10, and then that would get read as 1000. Basically, it gets turned around when you load it. So again, kind of backwards from what you'd think, but that's the idea. Is you go to FFFC and you put in your startup address, and when the CPU restarts, it's going to look at that address, grab the address you put in there, and then load that address and start executing code at that address. So I want to drive that home a little bit more because it is a little mind warping. Sometimes indirect pointers like that, or indirect addresses, are a little hard for people to wrap their head around at first, but it's just that you've got a location in memory that stores a location in memory, and you can kind of do that infinitely, right? But in this case, it's just two levels. So there's a location in memory that stores a location in memory. So it's like if you, at your house, here, let's say this. It's like if you had a friend and you said, hey, go to this house at this address, and there will be an envelope there, and on that envelope, sitting on their front porch, is going to be the address of the house I want you to go to, I don't know, deliver a pizza. So what they would do is they would go to the first house at the first address, 200 blah 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 street, and they would grab that envelope, and in that envelope they would pull it out, and that would say, go to the house at 503 West Doody-Doo Drive, and they would go to the house at 50 whatever West Doody-Doo Drive and deliver the pizza there. Same thing here. At FFFC is the address to start executing at. The CPU reads what's at FFFC, loads it, then starts executing whatever was there. So it executes the code at the second house. So if there's an envelope on the porch of the second house that contains code to start executing, that would be the same diff. That would be the idea. So we have a rough idea how to start it up. I also want to drive home, because I had questions last time about fully resetting the computer. Resetting the CPU is fully resetting the computer. So on more advanced computers, there are more, like, resetting the computer does more hardware things that reset more of your peripherals and stuff to known working states. But you can kind of ignore that bit, because when a computer starts up, it's kind of expected to be in a garbage state. Resetting a computer just means telling the CPU to jump to whatever its startup address is and start executing code there again. And the thing is, the code that's there is always going to be initialization code. Just, it can be whatever you want, but that's generally how it works. Is when this computer starts up, there's just random static noise in this RAM chip, because when it powers down, it loses power, it loses everything stored in there, and when you power it back up, it's actually not necessarily empty. You might think it's empty. It's just random noise in there, like static from the universe. Whatever bits got toggled when the thing turned on, that's what's in memory. And when you're writing computer software, you pretty much work based on that assumption. Is your hardware is in some random state, and you probably have to write some software to reset your peripheral devices. Your memory is going to be full of garbage, so if you want to use it, you're going to have to initialize it to some value first. So resetting the whole computer is really mostly done in software, and it really depends on what you want to do with the computer in the first place. Because if you've got, like, up to this point, we've done some stuff and there's just been tons of garbage in memory, but it hasn't affected us at all because we're not using that area of memory, right? We don't need it to be anything in particular. So there you go. That's a fun fact about this. Also, a lot of that resetting and putting the computer in like a working state for your day-to-day uses is operating system stuff. I want to drive home, again, this computer doesn't have any software on it until you put it on here. There's no ROM, there is no storage of any sort, except for the RAM that, you know, it blanks out as soon as you turn off the thing. There's no storage, there's no operating system on this thing, there is no code on this thing until you put it there, which we're going to do today. So, the first thing that I'm going to do, and this is an arbitrary choice, is I'm going to key in a startup address at that reset vector location, which again, that was at FFFC, again as we're practicing our hex, that's 8, 9, A, B, C, 8 and 4. So that's FFFC. And what I'm going to put there is actually a 0 first, because it's little endian. And then I'm going to put at FFFD a 2. So that's 1, 2, 4, 8. So this is 2. So now what I've stored is a 0 and a 2, which, when read as an address, will be the address O2. Whoops. Got to do the address, not the data. O2 O, right? Because it reads it in that order. And so what's going to happen is the CPU is going to start up, read that address, and start executing code from address 0200. And we can demo that again in just a second. But I chose that address somewhat at random. If you look at the 6502's datasheet, a couple of the other interesting, useful things to know are that generally the first 256 bytes of memory the CPU uses for what's called zero page. I won't get too deep into that because it actually gets fairly interesting, but you don't really need to know it right now. But things that are in the zero page are just faster to access, and it's something very particular to the 6502 CPU in particular. And then also, it should be noted, 256 bytes can be addressed by, or 256 address locations can be represented by 1 byte, right? Because 1 byte can represent the value 0 to 256. So 0 to OFF is your first 256 bytes. Then your next 256 bytes, which is used for the next kind of special area, is what the CPU uses for the stack. And we will, all CPUs have a stack. The stack on the 6502 is a little weird. Again, not going to get into it this episode, but that area is usually, I mean, it's hardwired to be used as the stack for instructions that utilize the stack. We're not going to use any of those. We're not going to use any instructions that utilize the zero page. We're not going to utilize anything that uses the stack. So we could just put our code at the beginning of memory. We could put it at 0. But just for consistency's sake, I'm going to start at 200 because that's the first location that the CPU doesn't have any special uses for. And that is just a special note on usage. But all of that said, just assume that I'm using address 0200 for no good reason, just because I chose it at random. So, back on the 6502 page, the next thing that we need is a reference for actual instructions, right? So I had the 6502 data sheet, and the data sheet, I mean, you can look at it. It does have instructions in it and information on them, and if this is good enough for you, then that's great. Like, this is just a description of all of the instructions that it supports: add with carry, logical and, arithmetic shift left, a whole bunch of different commands. But this is just like their names. This is just the table saying what things can you do on the CPU. What we actually need to know, and it is in here, is what the actual number that corresponds to that command is, so we can put it into memory and actually do something with it. Now, this is probably one of the harder ways to read it, and again, this is why I'm going to recommend using the resource that I've linked in the project page, because this actually does encode the commands, and what it's saying is the first byte is whatever's in this, and the second byte is whatever this. So 00 is the break command. I think this is the most significant and least significant, so I think it's this one followed by this one. So 00 is break, for instance. 24 is the bit command. But this is really, really terse and a little hard to read. So what we're going to use instead is this 6502 CPU instruction reference, which is just a nice resource that somebody made. I would love to give credit. It's at masswork.at. I don't know who in particular runs masswork, but as you can see, you have the same table here for people who want to read it that way. But this table also has links all over it. Each of these is a link. So let's say you want to look at, let's ignore these parts for now. These will make a little more sense in a minute. Or maybe I won't even get into those today, but they will make sense later. But let's say I want to look up what the number is for the AND command, which it actually is telling me right here with that pop-up. It's saying hexadecimal 35. In 6502 land, and generally kind of older computer land, a $sign before a number generally indicates hexadecimal. So, fun fact on that. But if you click it, it takes you down to this section of the page that gives you some information on it. The AND command is the mnemonic, which just kind of means the short form, like the short little name that corresponds to that command. That'll matter more when we get into assembly, but just know that's a human readable name that you can refer to it by. And again, it's basically arbitrary. But yes, so and memory with accumulator as a random choice. You can ignore a bunch of this, but the important thing is to check out this addressing mode and the opcode. So I've been saying the number of the instruction up to this point. The technical name for that is opcode. It just is short for operation code. You know, there's nothing like fancy and scientific about it. That's just like the official word that everybody uses for the instruction number. It's the opcode. On the 6502, it's really nice and convenient because every command that can be done by the computer is encoded in 1 byte, very conveniently. There are some computers where the instructions get a little more complicated. They can be multiple bytes or things like that. But in the 6502, that's one reason that it's a good learning computer, is that every command is 1 byte, or at least the command is 1 byte, and then there can be operands, which we'll get into in a second. But opcode is the number of the command. So when entering a command into the computer, basically what happens is when this computer goes to that start address of 200, once it's read the reset vector and says, all right, I'm going to start reading whatever is at 200, it expects to read a byte, which is an opcode, and it's going to do whatever that opcode says. And the CPU is just hardwired to always, you know, if it's 29, it's going to be an AND, it's going to do an AND immediate. And that's how commands work, is it reads the byte, reads any subsequent bytes out of memory that are operands, which again I'll get into in a second, and does it, and then moves on to the next command and does it again. And that's how CPUs work. It's just this constant loop of read a command and or any extra data that belongs to that command that's subsequent to it, and then once it's done doing that, it moves on to the next location and does that all over again. And we'll see how that works in a moment. But yeah, so the next thing to go into is addressing modes, because the AND command ANDs things. You know, it does a logical AND between two. Well, actually, it does a bitwise AND. Sorry, not a logical AND. But that's splitting hairs, and we'll get away from this command. That won't be the first one we use. It's just an example. But anyway, this is going to do a bitwise AND between two things. But there's a lot of ways to say what two things you want to use as the two sources of information. The 6502 is what's called a single register machine, which is kind of not true. It has 3 registers, really. But what that means is that every command implicitly uses what's called the accumulator as the place to store the completed value. So for example, if you're going to use this bitwise AND command, it's going to grab one of the arguments from somewhere, one of the operands, one of the 2 things going into the AND, X and Y. So it's going to grab that first thing from somewhere, and it's going to grab the second thing from the accumulator. And the accumulator is just a 8-bit storage space in the CPU that's very fast to access. That's why it's in there. It's faster to access for the CPU than memory. And so implicitly, everything always works with the accumulator unless it's an instruction that really specifically indicates something else. But most commands, it's implicitly saying do the operation and use the accumulator value, the current value in the accumulator, as one of the inputs, and it's going to store the result generally also back into the accumulator. Where it gets that second address is what this addressing mode is about. So there are several versions of the AND instruction. There's one that's number 29, there's one that's 25, one that's 35, and each of those correspond to a different addressing mode. So there's immediate. I'll dig into more of these later because it's not important right now so much, but you just should probably get an idea as we get into this. There's immediate mode, which has the command byte in memory, right? It's going to be 29, and then it expects the next byte to be the literal value to load into the accumulator, or to use as the other address or the other value. So if you did a 29 and then followed it by 10, what that's going to do is the CPU is going to read this command. It's going to say, oh, it's an immediate AND. Then it is going to increment the program counter and read the next byte, which was, I think I just said 10, and it's going to take that 10, it is going to bitwise AND it with whatever's in the accumulator, and then it is going to store the result of that back in the accumulator. And that's what that does. Now, that is the general operation of most of the commands on the CPU. They kind of follow that structure. Where it gets that data from is gonna differ. As you can see, there are different addressing modes for selecting different sources and different ways of referencing that other value. But the most straightforward example is immediate, where it's called immediate because the value to be used is immediately after that opcode. So if that was at address 200, it'll read that at 200, read the operand, the 10, from 201, and then when it's done doing that, it's going to start a new cycle of reading the next instruction, which is going to be at 202, and it just keeps incrementing and doing that as long as it's on. So let us start our easiest program. And that's going to be a loop that does nothing. So this is going to be a fun one because you'll see how a loop actually works in a machine. So if you've ever heard of goto, this is going to be very familiar to you because all the CPU can ever do is actually literally goto. There is no, well, it depends on the CPU. There are some weird ones out there, but you can generally assume that the way CPUs work, there's no for loop structure. There's only comparisons and branch and jump commands, and a branch or a jump command is basically a goto. So for example, let's look at one of the simplest branching instructions, which is jump absolute. So as you can see, again, there's a lot of different versions of the jump instruction, but all the jump instructions do this universally similar thing where they jump to a specified location in memory. So you can kind of think of the reset vector here as a jump command that the CPU just kind of does implicitly when it starts up and gets the address from a hardwired location. It's the similar thing. So the jump command, as you can see, this says the length of it is 3 bytes. You probably didn't notice because I didn't point it out, but the AND immediate example that I gave was 2 bytes long, which makes sense because it was the command byte and then the immediate value byte. For a jump, it's 3 bytes because you have the first byte, which is the actual jump command for C, hexadecimal, of course, and then you have 2 more bytes that are the address, stored that same way that we stored our reset vector, where it's going to be the smallest part followed by the biggest part in memory. And I mean, it's really that straightforward. What's going to happen is the CPU is going to read the 4C, say, oh, this is a jump absolute command. As you can see, there's another version of jump too, but we're going to ignore it because you just need to know we're using the 4C one, which is a jump to an absolute address. And then the address is stored immediately after this in 2 bytes. So it reads the next 2 bytes. So, you know, let's say, well, if we were doing a loop in this case, it's just going to be an infinite loop. Our code started at address 0200, right? Hex 200. So if you did 4C 0002, that's going to be a jump back to address 0200. And it's just going to then read that instruction again, read the address, jump to 00200, read the instruction, read the address, jump back to 00200, and it's going to do that forever. So our first program that we're going to do, and that's going to be the whole story today, is an infinite jumping to itself loop. But you'll get to watch it run, and I hope that it'll be fairly satisfying, because for once you're actually making this thing do some... saying it's doing some work might be a bit much, but it's definitely doing an action, running a program. So let's get over here and let's actually put that into practice. All right, so we've already put in, we can review. Right now I'm in program mode. I'm not in run mode. Run is off. And the address that I have inputted is still that FFFC, which is 0, and then FFFD is 2. So that's our 0200 startup vector. So now let's start putting in code at 0200. So we will go over to that address, set everything to zeros except for this 2. So that's going to be 0, 0, 2, 0. And right now, like I was saying, there's just some garbage there. Nobody put that in. That's just the memory is full of static from the universe. So what do we store there? We store our jump command. So it's going to be 4. So that's 1, 2, 4, 8, 4. And then it was C, right? It was 4C was the jump command. So 8, 9, A, B, C, 0, 0. So that's 4C. And now I'm going to store it at that address. Again, I want to drive this home. You guys have toggle switches. You're going to have to basically click this twice every time you do a deposit, because mine pops right back up after I'm done pressing it. Your switches toggle on and off, so you gotta do that. But now we have 4C stored in RAM at address 0200. Okay, now we got to put in the address for that command, because this command expects the next 2 bytes to be an address. So the CPU is going to read that command, and it's going to say I need to read 2 more things, and that will be the address to jump to. So let's go to the next address, 0201. And again, there's just random noise in there. And we put in, like I said, we put this in little endian, just like we did for the reset vector. All addresses in here, when they need to be stored as 2 bytes in memory, they are always little endian. The little part first, and then the big part. So we store a 0 there. Then we go to the next address, 0202. And there, I'm going to store 02. So let's review our contents of memory. So at 0200, we have 4C, the jump absolute command. Then at 0201, we have a 0. And at 0202, we have a 2, which again will be assembled as 0200 when the CPU reads it as a full 16-bit value. And that's it. I mean, again, we can review. If we go back to FFFFFC, again, that's our same thing. We have 0200, our startup address. So there's nothing to it but to do it. And another reminder that my single step button is kind of flaky, so we might get a couple of cycles. we'll just see how this goes. It might be bouncy. We might skip some cycles, but let's just do it. So now that we have that in memory, the only thing to do is to reset the CPU and start executing. So again, for people with toggle switches, which is everybody, the easiest thing to do is going to be to just toggle in your reset on your CPU, and that'll hold it in reset mode, which again, you need to do a few cycles of the CPU for it to fully and properly reset. For me, I'm going to have to hold it down because I have a temporary button, not a toggle button. But no, for you, you can just toggle it on and off instead of holding it down. Now I'm going to make sure my speed toggle is set to manual. And finally, I am going to switch over to the CPU. And now the CPU is in control. The clock is going to be coming from this button because we're in manual mode, and I'm holding down reset, so the CPU is in reset. It's not going to do anything. Every time you clock, it's just going to keep itself resetting to its default state. So I'm going to give it a few clocks. And now I'm going to release my reset button. And now we can actually start stepping through. So as I said in the last episode, but I don't know if I was clear enough about it, it takes a few cycles. It's always the same number of cycles, but I don't know what it is off the top of my head, for the CPU to actually get to the part where it's going to read the startup vector out of memory. And we'll just see how many that is, and we can count it, I guess, but it doesn't matter. The main thing is just look at these address lights, because you'll see it'll be fairly obvious when it suddenly puts FFFC on here, and you'll go, oh, okay, we've gotten to the part where it's trying to read the startup address, so let's do that. All right, so again, there's just kind of, I don't know what this is on the address bus, random junk. But there we go. Now all of a sudden it's FFFC, and that's gonna read the byte from FFFC, which is 0. If I press it again, now it's reading the one from FFFD, which is our 2, so it's gonna be 0200. And now, if we bop this real quick, look at that. The address is 0200. It grabbed that address, put it into the program counter in the CPU, which is the register or storage space in the CPU that always points at the next instruction to execute, or the next thing for the CPU to get out of memory. And we're seeing that on the address bus, 0200, and then we are seeing at that location 4C, our jump command. Super cool. All right, let's keep going. So now it reads the next address to start loading the immediately following address that's being specified for the jump command. And it reads our 0 at 0201. And now it's reading our 02 at 0202. And it went back to 0200. And if we just keep doing this, it's just going to do that forever. 1 2 0 1 2 0 1 2 0 1 2 0. And so that's it, just executing one instruction over and over again. And that is an infinite loop. You have successfully inputted your first machine code CPU command. As you can see, it's not very consistent. That's the bounciness of my switch. But there you go. There is your first program that you have written on bare metal. Feel very proud of yourself. You know, nobody does this crap, so good on you if you have gotten this far. And then, for shits and giggles, we can switch the clock and speed it up. So generally, whenever you switch the clock source, you're going to want to reset the CPU, because if you toggle and it's switching from one clock source to the other, there can be like a bunch of noise when it's switching, and it might just do weird things that you're not expecting. So generally, best practice just to reset the CPU first. And now I'm going to put it in slow mode, which is, of course, where the clock is controlled by this knob over here. As you can see, the clock blinking away over there. When it's turned all the way to the left, it's pretty slow, like maybe toggles once every 2 seconds. But then you can really speed it up, and it'll go fairly fast, probably into like the kilohertz regime, to the point where you can't see it blinking anymore with your bare eyes. But it is, I promise you. And so now that we've got it in that mode, if I release the reset button, or you toggle your reset button off, it's the same thing as when I was doing it manually, but now it's we've got a nice regular clock, and I don't have to keep pressing that button. And we can watch it doing the same thing. There's it reading the address, and here's it doing the cycle. 0, command, 1, 0, 1, the part of the address, 0, command, 1. There's the command, there's our 0, there's our 2, there's our command, there's our 0, there's our 2. And we can speed this up if you want. And there you go. It's doing it at probably a few kilohertz. I don't know what the actual top speed of this thing is. And if you want to go really crazy, you're not really going to see anything different, but let's hold down the reset button again and put it into full speed mode, where it's going to run at a full 5 megahertz, which is pretty flipping fast. That's 5 million clocks every second. So there you go. It's the same thing. And you know, it's nice stable code because I'm sitting here talking for several seconds, and so therefore we can determine that there have been several 5 millions of cycles executed, and it's still just doing that same loop, because computers are dumb. They just do whatever's in memory. And that's it. You've put in your first program. I will cut it off here because this has already gone over half an hour, but have fun with that. Look up more commands if you want to. From here on out, we're just going to be exploring more different instructions, more of the architecture of the CPU. But this is the basis of things. You've learned how to put stuff in memory. You've learned how some of that stuff can represent numbers. You've now learned how some of that stuff can represent commands for the CPU to do. And also implicitly, I think this is worth pointing out because people maybe don't notice this sometimes. What we've also implicitly shown is that there's no difference between code and data in memory. The CPU doesn't know that something is an instruction, except that it just expects an instruction to be there at a certain time, right? Like 4C can be a number. That's going to be like 4 times 16 plus 12, whatever that number is. 32, 64, what is that, like 76, something like that. So that can be represent 76 things, or it can represent a jump. It only depends on what the CPU expects it to be at any given time. So for example, when it jumps to the location where it's going to be executing the first command, then it's going to assume that that's a command and it's going to treat it as such. And then the next 2 things in memory are also just arbitrary bytes, but the CPU expects them to be addresses, and so it reads them as addresses and uses them in that way. So there is no difference. The CPU cannot tell what is a number and what is instructions, except when it's, executing them in the order that you specified and are expecting it to do. So that's just a side note too, that if you put stuff in slightly wrong, your CPU will probably blast off into space, and you're going to get like absolutely, you'll have no idea what's going on, and it will look like absolute garbage, because this is in this stable loop because our instructions are actually lined up right. The entry point is at 200. We put in our first command at 200, and then we wrote that command to jump to 200, where it's going to expect another command, and so on and so forth. So it's stable. It's always going to do that loop. But most things in memory, like if you just take random numbers, are not going to be nice, stable commands or loops or sequences like that. So if your lights just, you're trying to do this and they're toggling all over the place, it probably means you didn't put the command in at the right location that it expected, or you didn't put in the right command, or something like that. So that's important to note, is that can be a kind of frustrating thing when you're first working with a computer at this low level, is that if you don't put in things just exactly right, like the CPU expects, it's gonna turn out like absolute chaos. And that's just the way it is. So know that if things are going chaotic, it probably means you didn't put in things just right. You absolutely need that reset vector to be in the right order at the right memory locations, and then you need the address that it points to contain a command that's, legitimate, and for that command to actually do something useful and not blast off into space. Also, one last thing, I'm going kind of long here, but the CPU doesn't know where to stop, right? There's no, we'll get into that, because there actually are some instructions, like halt instructions, where the CPU actually will stop executing code. But that's a really specific case that there is a specific instruction to do that. But in general, it's like the CPU doesn't know where to end, right? It's not like, say you wrote a program and it's got the main function or whatever, and it executes and it goes into the main function and it like prints hello world or whatever, and then it hits the end of the function and it exits, right? It doesn't work like that here. When your computer compiles that program, it's, you know, putting an exit instruction and an instruction to jump back to the operating system at the end of that whole thing. If you just, like, let's say, and maybe I'll get into this specific example next time, if you just put in an add command at the first address here, it's going to do that add command, and then it's going to go and move on to the next instruction, and if that instruction is garbage, it's going to start going off into outer space for the same reasons that I said. So it's not going to just like nicely stop after that instruction. It's going to keep plowing forward. So if you're going to do something like that, you'd need to put like a jump or something, or like an infinite loop after that for it to just like hang after you've done that. And we'll do that next time, but it's important to note, because if you're trying to play with it after this and you encounter some scenarios like that, that's another thing that like isn't intuitive usually, is that you know, your CPU is just going to keep on executing. It's not just going to like stop unless you absolutely tell it to. So, okay, that's enough for this time. Next time we will get a little bit more advanced, maybe actually make a program that like does something. Sound good? All right, I will see you guys then.